In the context of state space systems, we've already talked about the concept of state feedback and also the idea of using the output to build an estimate of the state in order to use the estimate for feedback. In all of that discussion, we talked about the idea of using a control law like U is equal to Kx, and we were always given the control gain matrix K. And so what we're going to be talking about in this upcoming class will be how to design or select K based on certain criteria. So again, for state space systems, we use a model that's x dot is equal to ax plus bu. And so this is B, and this matrix here is A, and those represent the state matrix and the control matrix. And when we talk about state feedback, we'll talk about feedback of the form where we select this input U to be of a specific form, a gain matrix K. So it's a matrix of constant values that we get to select. And it's going to be proportional then, it's multiplying by the state X. And so we've seen this already, how this plays out for our spring mass damper, which again has a matrix A that looks like this and a B that looks like this. And when we use this U and we substitute this definition of U in here, that results in a closed loop system that looks like x dot equals A plus BK times X. And the U term is gone because we've substituted KX in there. And so now the stability of this, this closed loop dynamical system is given by the properties of this matrix A plus BK. And so he said that the real part of the eigenvalues of this matrix need to be negative. And so it's pretty straightforward then that if we wanted to make a system stable and we didn't know this gain yet, we get to select this gain K. The gain matrix K, then we would design it such that the eigenvalues have negative real part. And so we're going to look at this spring mass damper as a motivational example, but it really demonstrates the procedure that we use in the process of what's called pole placement for designing that feedback control gain. So in this particular example, A plus BK is just given by A, and then we multiply B by K, and this produces a matrix that has zeros in the first row and K over M terms in the second row. And that just yields a matrix A plus BK that looks like this. And so we want the eigenvalues of that matrix to have negative real part. So our job is to just compute the eigenvalues. And even though there are still some symbolic things that we want to decide, like K1 and K2, we can still compute the eigenvalues in terms of those. And so we just compute, again, the matrix, which in this case is the whole thing, A plus BK minus lambda I. And so these bars here denote that we're taking the determinant of this matrix, and that produces this quadratic in lambda, where lambda are the eigenvalues. And so the ones that set this equal to 0, again, equal to 0, are the eigenvalues. And so we get this quadratic. Once we simplify this a bit, we collect all our terms. And so this is the quadratic that we want to make equal to 0. And so the roots, lambda 1 and lambda 2, are the eigenvalues. And we will make sure that those have negative real part. Or what we're going to do here is we're actually going to select where we want those eigenvalues to be. Or remember, that's equivalent to saying where the poles will be. Poles and eigenvalues are the same. And so if we want poles to be at some value P1, for example, we could assume that we wanted to make this minus 2 plus or minus 4i. So that would mean that P1 would be minus 2 plus 4i, and P2 would be minus 2 minus 4i, for example. But again, you can specify where you want these poles to be, and let's just say it's P1 and P2. And so that means that this characteristic equation, or the characteristic equation for the poles, would go like this quantity S plus P1 times S plus P2, which would give us the characteristic equation like this. And remember that the eigenvalue equation, when we studied this for open loop systems, the eigenvalue equation here was identical to the pole characteristic equation here, essentially the denominator of the transfer function. And so that means that this alpha 1 needs to be the same as this coefficient here, the linear coefficient. And then the constant coefficient here, alpha 2, needs to be the same as this coefficient here. And so if we do those equalities, if we set the matching coefficients equal to each other, then we can then solve each of these, the system of equations, in case there was a system of equations, for the gain values k1 and k2. And so alpha 1 and alpha 2 are things that we know from picking our poles P1 and P2. So as soon as we pick our poles P1 and P2, we can compute alpha 1 and alpha 2, which would then allow us to drop that into these expressions, and that would give us the values of k that would make the matrix A plus BK have eigenvalues at exactly P1 and P2. And so this is going to be the notion of what's called pole placement, and we'll dive into this more in class.